Going to So you should be able to see my screen. Hi everyone, I am Clara. I am a PhD student at McGill University. Today I'm going to talk about optimal spectral norm approximate minimization. So the content of this talk is based on two papers. The first one will be presented next week at ICAL, and the second one at the end of the summer at ICGI. So this is a joint work with Borja Balle, Guillaume Rabousseau, Prakash Panangaden, which is my supervisor, and my co-supervisor, Dorina Prekap. So the contributions that we make with those papers are all centered around the approximate minimization problem, which we tackle using AAK theory, which is a theory for uncle operators that uses tools from complex functions approximation. So in the first paper, we applied this theory to provide a closed form solution and an algorithm for a class of weighted finite automata on a one-letter alphabet. And in the second paper, we extend this result to general black boxes for language modeling, still on a one-letter alphabet. So during this talk, after the motivation, I will spend a good share of time reviewing AAK theory. So I will try alpha way, and at the end of this very long session to do a quick recap to set the things that are really, really important to understand the contribution. So hopefully it will be clear. And afterwards, I will present the ICALP submission. And very unlikely, but maybe if there's no question or if I speak very fast, we will say a few words about the ICGI submission. So what is approximate minimization? So the approximate minimization problem is concerned with finding a model which is smaller than an original given one and imitates its behavior while minimizing a certain measure of the approximation error. So for example, we can think of being given a minimal WFA, and we want to find another automaton which is smaller in size, so it has less states, but imitates as best as possible the behavior of the first one. So this is particularly useful if we're trying to reduce the computational cost, to do model compression, or even just to increase the interpretability of the model, to understand what's happening with a certain input. The first big decision that we need to make when we are trying to tackle one of these problems is how we are going to measure the approximation error, because this is going to be the big decision that shapes the full problem. Of course, there are several norms that can be chosen. The one that we selected is the Spectral-Norm, which is the biggest singular number of the uncle operator associated with the model. We will see these later in the background. So the reason why we chose the Spectral-Norm is that it has some very desirable theoretical properties. So first of all, it is not model specific. Now, this is not as interesting, I guess, if we're trying to minimize an automaton with another automaton. But if we're trying to use a WFA to approximate a black box or a neural network or another class of models in general, having a norm that does not depend on the architecture or the specific behavior of the model, but just on the input-output behavior, it is certainly an asset. So this is an advantage. Another very important point is that we can find the best approximation. So the Spectral-Norm allows us to find the optimal WFA that produces the minimal error. And we can compute with precision the error, and we can do it in a relatively efficient way, because we will show that our algorithm is O of n cube. So it is reasonable. And finally, all of this is possible thanks to the fact that the Spectral-Norm gives us a connection with AAK theory, which is this theory I mentioned before that we are going to soon introduce, that relies on complex functions. So part of the talk will be devoted in trying to build some kind of bridge between WFAs and complex functions. So first of all, just to set the definitions, when I talk about WFAs, weighted finite automata, is a triple that is defined over an alphabet sigma and is characterized by two vectors, the vector of initial and final weights, and a transition matrix which is defined for each element of our alphabet. So we're only going to consider WFAs with real weights. Our contribution can be extended and adapted with complex weights, but not with weights in any other kind of rings. So this is important to keep in mind. So the functions that our WFAs are computing are functions that assign a real value to a sequence. So a class of weighted automata that we care about are generative probabilistic automata. So this will be an example that we will make during our talk. Those are automata that are computing a probability.
Clara, sorry, just a quick question. Prakash was asking if you could clarify. You said it's easy to compute when you were talking about the spectral norm. Were you talking about computing the spectral norm or actually the minimization with respect to spectral norm?
Both. Excellent. We can return the optimal solution and we can compute with precision the value of the norm. In the case of WFA to WFA, in the extension, not exactly, but still precisely.
Thanks.
You're welcome. So, okay, so I've been talking about minimizing a WFA. So what I mean here is try to minimize the number of states. And we're going to do this by working on a matrix, which is called Hankel matrix, which is attached to any function that look like sigma star to R, so that assign a real value to a string. So all the time we have this type of functions, we can build a matrix which is Bay infinite and has rows and columns that are indexed using strings from the set of strings. And the value in the matrix is the value that the function take on the concatenation of the strings. So this matrix is characterized by a property, which is the Hankel property, that is summarized in this example. So if we take two pairs of strings that are distinct, if their concatenation produces the same word, then the value that is going to be stored in the Hankel matrix at those entries is going to be the same. So this means that the value in the matrix depends only on the concatenation of the coordinates. So this is a very defining property. And there is a relation between WFAs and Hankel matrices. So we have that if we're given a function from sigma star to R, this function can be computed by a WFA if and only if the rank of the corresponding Hankel matrix is finite. In which case we have that the rank is the number of states of the minimal WFA that we need. So we can see there is a clear correspondence between states of a minimal WFA and rank of the Hankel matrix. So our the idea is we start with an automaton that is computing a function. So we know the input-output behavior, and we can use it to fill this matrix. This matrix will have a rank which is equal to the number of states of our original WFA. So we are going to do some low rank approximation on this matrix to be able to obtain a smaller matrix corresponding to a smaller WFA. So this is what we are going to do. There is a well-known result in low rank approximation that says that the best low rank approximation is obtained by truncating the SVD. So you give me a matrix, I compute the SVD, I throw away the bits I don't care about, and I obtain the best result, which is the singular value at position k+1, because I'm counting from 0. So this would solve our problem, but unfortunately, truncating the SVD does not produce an Hankel matrix. And we do need this property because it characterizes matrix of WFAs. So if our truncated SVD is not Hankel, we cannot recover a WFA from it. So then the question becomes, okay, we need to search the best approximation within the classes of Hankel matrix. matrices. So how is this going to affect our approximation error? So somehow, surprisingly, what AAK theory says is that the achievable error does not change. So if we are looking for the best approximation within uncle matrices, instead of in the full set of finite rank matrices, we can find an optimal solution that will return the same error as the truncated SVD. So this is fantastic because basically it tells us that there is a hope to solve our problem, to find the best solution, recover a WFA, and leave happily afterwards. The only issue here is that we need to do a bit of construction to use this theory, which will come with a few intense assumptions. So we are diving immediately into the first one, which is needed to be able to define uncle operators. So I will talk a bit more about this assumption during the time of the talk devoted to the contribution, because we will need this assumption all the way there. But basically, we need to restrict to one-letter alphabets. So this is needed because we want to be able to embed sigma star, which is the set of strings, into the set of natural numbers. We do this by associating to each words the number of times the single letter appears. So we want to be able to do this to make the passage between sequences and complex functions. We're going to see immediately why. So from now on, all the time I talk about a function from N to R, we can think of a function computed by a WFA over a one-letter alphabet. So in this setting, we can look at the uncle matrix like the representation of an operator that we call uncle operator with respect to the canonical basis of the complex, of the space of sequences over N. So now the uncle property becomes that a value in the matrix only depends on the sum of the coordinates, because now we're dealing with natural numbers. Just a little parenthesis. I've been talking about SVD and I've been talking about an infinite matrix. So to be a bit more precise, there is a construction that is called Hilbert-Schmidt decomposition that generalizes the SVD in this infinite matrix setting. It is defined all the time we have a compact operator. So this is also going to be a bit of a returning theme. And all we need to know is that what before in the SVD were our singular values, now are our singular numbers, and they play the same exact role. So it's the same role that is covered by singular numbers. So intuitively, we can just think of singular values. And the other important thing is that all the time we have a finite rank matrix, we can compute with precision exactly the singular numbers. So if our uncle matrix is finite rank, we can have the exact value of the singular number, even though our matrix is infinite. So this is an important point.
And do you have finitely many of those singular numbers, or you may still have infinitely many?
So you may still have infinitely many. If your operator is compact, they are converging to zero. If it is finite rank, you have finitely many as the rank, but they might be infinite. So the fact that we can compute them, it's important because this is basically what we are going to link to our norm. So the spectral norm is the largest singular number of an operator. So if the operator is a finite rank, we can compute this norm, is what Prakash was asking before. We can actually compute the exact value of the norm. So now we need to find a way to go from sequences to functions. So first point is that now I'm talking about sequences over Z, whereas before I was on sequences over N. We just duplicate the sequence. This is just an embedding in position 1 and -1. I will have the same value. The big deal is now jumping to the set of square integrable functions on the unit circle. So to do this, we are going to use the Fourier isomorphism. So on one way, basically we start with our sequence, we attach to each element an element of the basis of the complex function space, we take the sum, and we have a function that is dependent on the complex variable z. I wrote it there just to avoid confusion. And on the way back, I take a function in my complex function space, and I compute the Fourier expansion. I obtain the sequence of its Fourier coefficients, and this is the sequence that I'm going to attach in my sequence function space. Yeah, sequence space, I'm sorry. So basically, I have a way to go back and forth using the Fourier isomorphism. And this is going to be a bit what we are going to use to go from functions over sequences to our uncle operators that live in the complex functions world. So the use of the Fourier isomorphism kind of split our function space in a natural way. So on one side, we have the subspace that contain functions only having positive Fourier coefficients. And on the other side, we have the negative RD space that contains functions only having negative Fourier coefficients. So what's important here is just that all the time we have a function, we can look at one of those two components, the component that lives in the RD space that represents all the positive Fourier coefficients, and the component that lives in the negative RD space that represents the negative Fourier coefficients. So a last disclaimer, because I have provided all these definitions in terms of unit circle because they are much more intuitive this way. But soon I will start talking about poles and singularities inside the unit disk, which might raise some eyebrows. The point here is that the element of those hard spaces, so those functions that live on the circle, can be identified with certain functions that live inside the complex disk. So we can actually make this passage because there is this identification. Alrighty, so we can finally define uncle operator with respect to complex functions, and then I will give a quick recap of what's important in this part. So we consider our complex function, and we define an operator. So what this definition is saying is basically that the uncle matrix of this operator is defined using the negative Fourier coefficient of this complex function that we call symbol. So all the time I have one of those complex functions, I can take its negative Fourier coefficients and use them to define a uncle matrix. So this is saying that the symbol is not unique because two functions that have the same negative Fourier coefficients, even if they have different positive ones, are still going to be defining the same matrix. And it gives us a way to link a complex function to a uncle matrix. So let's summarize a little. We start with our function that goes from n to r, which can be computed by a WFA over a one-letter alphabet. So this function can define a uncle matrix. So we can use it to fill the values of this uncle matrix. The value of the uncle matrix is the value of the function on the sum of the coordinates. So this is the standard WFA-friendly way of looking at it. Now that we have this uncle matrix, we can actually associate with it a complex function that we're going to call symbol that is also linked to the entries of the uncle matrix, this time by means of its negative Fourier coefficients. So we can see when we have a uncle matrix, we can pick which of the two interpretations we are going to use, depending on whether we look at the entries with respect to the function f or with respect to the function phi. And those two functions are actually related to each other. So this is really all that is important to remember out of everything that I've said right now, is that this this dual way of looking at the uncle matrix is going to be the key to go from the WFA interpretation to the symbol-friendly interpretation that is where the AAK theory lives. So we're going to switch and go in these complex functions, use this AAK theorem, get our hand dirty, and then come back to the WFA world and forget about it. Okay, so let's see quickly an example. So we can consider a WFA that has two states. We have still a one-letter alphabet. We have our vector of initial and final weights. And this WFA is computing a function that we can check is actually a probability. So this is a generative probabilistic automaton. So we can use this function. We have its behavior on any input. So we can use it to fill the entries of our uncle matrix because they're just depending on the value of the function. So now that we have this matrix, we have the actual entries, we can look at them with respect to the symbol because it's the same. And so we can use those values to recover the negative Fourier coefficients of the symbol. So to do that, we consider the projection on the negative RD space, which just means negative Fourier coefficients. We know how they look like because we have the values in the function. And so we can compute kind of the function representing the negative Fourier coefficients that we call rational component because it's just a quotient of two polynomials. Okay, so we are finally at the AAK theorem. So before I gave a quick spoiler talking about matrices of we can find the best approximation within the class of uncle matrices. This theorem is actually stated for operators, but the idea is the same. So we have a compact uncle operator, compact so that I can compute that kind of SVD. It has a matrix H, and we can find a unique uncle operator with matrix G with the property that it is the best spectral approximation. So each of those two operators is defined with respect to a symbol phi and a symbol G. So last background slide, we take out the heavy artillery that we need for our contribution because the formulation of the AAK theorem that we use actually speaks about the symbols. So it is equivalent, but it is stated in terms of those complex functions. So what it says is that, so first we have a bound in the complex function space. So it's no more spectral norm, it's another norm. We don't really care about this right now. What it's saying is that if I have the symbol of my uncle operator, which is associated with the uncle matrix of my original WFA, I can find a function C that is also a complex function that attain this bound. So what is interesting for us is that the proof of this theorem is constructive. So it gives us a recipe to build C, and it tells us how it looks like. So it looks like the sum of two other functions. One component that has only positive Fourier coefficients, that behaves well around the unit circle, no poles inside, everything is fine. And another component G that is rational, so it's a quotient of polynomials, and behaves poorly in K points inside the unit disk. So what is beautiful here is that this component G is actually the symbol of our best operator approximation. So we can see that we're going to start with WFA, build the uncle matrix, get a uncle operator, get a symbol, then use this AAK symbol theorem. It's going to return a function C. We will extract this G component and use it to define the new operator, the new matrix, the new WFA. Alrighty, so we made it through the AAK section and we can finally talk about our iCalc contribution. So in this setting, we are given a minimal WFA, which is as n states, uncle matrix H with rank n. We have a target number of states, and what we want to do now is to find a WFA which has a matrix G of rank K that is the best spectral norm approximation which solves AAK theorem. So to apply AAK theory, we need a few assumptions. So here it's the miserable part. As I already mentioned before, we need to be able to embed sigma star into Z. Because if we do not embed sigma star into Z, we cannot use Fourier theory. We cannot go to the symbol, we cannot get our solution. So we need to be able to do this. So if we have a one-letter alphabet, sigma star, it's a free monoid, can be embedded into N, then we go to Z, and everything is happy. If we have more than one letter, we get a non-commutative structure. So good luck embedding these into Z. And so we cannot use the Fourier isomorphism. So we are going to see at the end how, if we can get rid of this hypothesis. It's a pretty big one, but this is a first good step, I like to tell myself. So the second assumption that we need is that we need this operator associated with the uncle matrix to be compact. This is because we need to be able to compute that SVD-like decomposition. So to check that our operator is compact, it is enough to show that it's finite rank and bounded. So finite rank comes from free, because we have seen WFA means finite rank uncle matrix, means finite rank operator. Nothing to do here. Bounded means basically that the entries of our uncle matrix needs to go to become smaller and smaller and tend to 0 as we go towards infinity. So not every WFA has this property. So to make sure that this property is there, what we require is we want the transition matrix of the WFA to have a spectral radius smaller than 1. So this means that we have a one-letter alphabet, so we have only one transition matrix. The eigenvalues of this transition matrix need to have absolute values smaller than 1. So a class of automata that satisfy this property are generative probabilistic automata that I defined before. And so this assumption is needed. We will see soon why. It is possible to get rid of it, but we won't be able to find the best approximation anymore, which is a bit of the nice part of this whole construction. So that's why we keep this assumption. So the plan that we are going to follow is this. So we have our WFA with n states. First thing, we want to compute a symbol. So we want a complex function attached to our WFA so that we can use the AAK magic. Then we want to use AAK theorem to find the function psi that is solving that bound that I brushed quickly through. Once we have psi, we want to extract what I call the rational component, so the negative Fourier coefficients part, G, and then we want to find a WFA representation for this function G. So this WFA is going to be the best approximation of our original WFA. So the first part, it's easy. We want to attach a complex function to the WFA, and this is what we have seen very quickly in the example. So we have WFA, it's computing a function that we know. So then we have these two ways of look at the uncle matrix. So on one end, we have the one that we can fill with the values of our function or from n to r. And on the other, we have the formulation that depends on the negative Fourier coefficients, which is what we want to get. So now we can actually find these negative Fourier coefficients because we know like how the function look like. So we can write these negative Fourier coefficients with respect to the parameters of my WFA. And actually this last equality, like we have this convergence because of the assumption on the spectral radius of the transition matrix. So we have a nice way to write this negative Fourier expansion of the symbol. Now you're going to have to trust me on this one. When we have a bounded operator, it is enough to have a bounded symbol. This is a very well-known theorem in functional analysis that is called Nehari theorem that says even if you have only the negative Fourier coefficients, if they form a bounded function, you're good. No need to consider anything else. And this is the case here because of our assumption. So these can actually be considered as the symbol of our WFA. We have a nice way of writing this. And now we get to the difficult, the most challenging part of the paper, which is how do we represent those complex functions? Because we have this way of constructing them with AAK theory, but that is not really helpful if we're trying to get a WFA out of it. So we need to find a nice way to represent C, which is the solution of the AAK theorem, and E, which is the difference between symbol of the original WFA and the solution. So we decided to do this using two WFAs. So basically, we're going to attach a WFA to each of those two functions. The first WFA, A hat, is defined to respect three properties. The first one is that it needs to have at least as many states as the target best approximation. So it needs to have K or more. Then one cannot be an eigenvalue of its transition matrix. Now, all this looks very artificial. Next slide, we're going to see why all those constraints are needed, but one cannot be an eigenvalue of the transition matrix. And the last constraint is that the second WFA that we define using A hat, and that we can see it's computing the difference between the function of the original WFA and the function of A hat, needs to be minimal. So A hat can be anything as long as these three properties are satisfied. Why do we need all these? So the idea now is that we use the parameters of our WFA to define the function C, and the parameter of E to define the function E. So we link all the parameters of the WFAs to our functions, and now we want to solve and find the parameters of A hat so that the bound of AAK theory is respected. So we want to find the parameter of A hat so that C is the solution of our AAK theorem. And now those constraints make a little bit more sense because, for example, we can see that from the way we defined, and this is a bit of the key point, the points in which these functions can behave poorly are all corresponding to the eigenvalues of the transition matrix. So, because this is our little denominator, so here, where I have an eigenvalue of A hat, I have a pole. And so, if we remember, our AAK theorem was saying that this function needs to behave well around the unit circle. If it behaves poorly, it can only do that inside the unit circle. So in terms of eigenvalues, what that means is I can have eigenvalues inside the unit circle, maybe so with modulus smaller than 1 or with modulus bigger, but not eigenvalues equal to 1, which is why we needed that assumption. So that needs to be respected so that this is actually a solution. And the second assumption is needed to actually check the same property here and rewrite these AAK theorem bounds in terms of the parameters of the WFAs. So I'm not going to get into the detail of this because it's pretty much just a bit of involved algebra on the constructions of the WFAs. We use the Gramian matrices. It's really nothing fancy. But the idea is that by assuming, by keeping general the definition of those WFAs, we can find the parameters so that C is the solution, that we know how it looks because the proof of AAK theorem is constructive. So I can get the parameters of A hat. Okay, now though, A hat is not the best approximation. We thought we were done, but we're not. So intuitively, A hat is too big. I have picked the size to be at least as big as the best approximation. And the idea here is that A hat is linked to Psi. But what we care about is just a part of Psi, is the part that has is rational with k poles inside the unit disk. So A hat is to B, we just need to get a little part of it, and we are going to have our best WFA. How do we find this part? Well, I go back. We have this definition of C. We only care about the rational component, which only has poles inside the unit disk. So we have defined this function to have the poles located where the eigenvalues of the transition matrix are. And so all that I need to do is to look at the position of the eigenvalues of A hat. And so this is what we do. We do a block diagonalization of A hat, and we just select the part that has eigenvalues with absolute values smaller than 1. So this is going to be the transition matrix of the best approximation. So to summarize a little here, well, we prove, because this looks a bit like a bit hands waving, but we do prove in the paper that this is actually the best approximation. And we provide an algorithm to compute this that does not really depend on all the AAK theory complex function part. Is really thanks to those bounds before, we could find a closed form solution. And that's all that the algorithm is computing. We give it a set of equations that is computing starting from our original WFA with the target number of states. So it computes the parameters of A hat, and this is just matrices multiplied to each other. And then it's doing this block diagonalize part to return the best approximation. So we show that this is the best approximation. We show that the error that is attained in the spectral norm is actually the optimal error. And for free, we even get a bound on the L2 norm of the difference of the functions computed by the WFA, just like that. And so this is basically a way to find the best approximation using AAK theory for a class of weighted automata that correspond to bounded operator, so with this property on the transition matrix, and defined over a one-letter alphabet. So in terms of future work, well, the first obvious point is trying to get rid of this one-letter constraint. So this is what we are working on right now. It requires to use tools from non-commutative functional analysis. So there is a version of AAK theorem for non-commutative operators. It's a bit ambitious. Like right now we need to find a way to adapt this theory to the setting of WFAs. And on top of it, this theory is non-constructive. So we will also, once we adapt, try to find a way to make these constructive, to generalize. So it's going to be a big next step. And once we've done this, it will be interesting to evaluate how good is actually the spectral norm, because it has some very desirable theoretical property, but we still don't have a real sense of how it compares to other more mainstream norms like word error rate for NLP community or behavioral matrix. We really don't know. And so these will be meaningful once we have experiments to do or study to do with more letters. And finally, apply this method to other classes of models. So this is what we have done in the one-letter case in the ICGI submission, in which we basically just got rid of the finite rank constraint. So it's no more WFA that we start with, it can be any black box. And the challenge there is how to deal with this infinite rank uncle matrix, for which we cannot compute precisely all the values, the singular numbers. It requires a bit of care in dealing with this issue. But we have done this first step in this ICGI submission. Now, I do not think I will have the time to talk about the ICGI submission, but if you have any question, I will be happy to answer on this part.
So first of all, thank you very much, Clara, for this very nice talk. Let me just stop the recording now.